Thank you very much. It's a great pleasure to be here. And thank you for the small souvenir, which doesn't look too small to me. So I'll give here 4 lectures according to the rule. So I'll talk about multiscale problem, which is a challenge then in numerical analysis. So these would be computational lectures. And we'll start with something that is of a more general nature and do one particular item there. And then I'll come to the others, what they will be. So the next one will discuss more particular approach, a framework for resolving numerical methods, where you try to reduce the number of unknowns, the number of degrees of freedom in the algorithms that you provide. So that is, of course, the large challenge in multiscale problem, that you need to represent so many scales over the domain that you have. So that would be there, and partial differential equation will be there. I'll mention that because today we will look at an ordinary differential equation in order to sort of kick this off in the setting. So this would be the second lecture. The third lecture will take a problem also in the multiscale business, where we start off with resolving all scales. So not sort of the process of trying to finding a shortcut so they don't have all scales. But this is a problem which is wave propagation, where we think we need represent everything. And the question then comes to reduce the number of floating point operations instead. The first was just the amount of unknowns. Here we have given a large amount of unknowns. How do you do that? And that will be a low rank compression of the discrete operators that we are dealing with. So that is, of course, in line with the data science approach of reducing the number of operations that is needed. But here we will use the fact that it is wave propagation. So a lot of the ways of doing that and how to do that is guided by the analysis of the feature in wave propagation. And only at the end, where we have know what to do, then we kick in with the compression methods, singular value decomposition or fast random singular value decomposition at the end. But after this, so that would be the third lecture. And the fourth lecture will be one particular application, and that is inverse problems in seismology, which is a Texas problem here. That's where the wealth comes from, is the understanding what is down there in the earth. And of course, also there are multiple scales, and that's the challenge of the problem. You are not looking for a few parameters in the inverse problem, but for a million. You would like to have the full field of the geological properties, typically something like just the velocities or the elastic parameters in that case. The many degrees of freedom in the problems comes, or the highly multiscale features come both from high frequencies relative to the size and from the variation, the layers in the earth that is in there. And then, as you know, when you have let's say you would like to match two high frequencies, sinusoidals, if you skip a wavelength, it looks very much the same. That's what the periodicity is. And that is a cause of difficulties in doing the inverse problems. It's in this business called cycle skipping. And that's where we use to try to break that, instead of using L2 and similar measures for comparing the data with your prognosis. We use a Wasserstein distance and see properties of optimal transport in doing this case. So that's what the other ones would deal with. So so today we'll call multiscale modeling in general. So I'll take some brief introduction part of the challenge that is there. And then we have two sort of theories that guides us for this particular approach that we'll come to mainly in tomorrow. One is based in information theory and how you can represent multiscale functions, and the other is one of many theories in mathematics that takes us from a problem with many scales into one with fewer scales, like homogenization. Here we'll use averaging in a simple way, and then we'll see how to build a numerical method on top of that, based on that. That's the approach. So, of course, intuitively we know very much. Let's see how this works here. No, this doesn't. Here we are. So there it sits. We know very much what a multiscale problem is in this sense. So we take as an example the aircraft flying, where you have the scales of the airplane and the overall flow patterns on the meters to hundreds of meters. And then we have the small variation in eddies in the turbulent flow that is important, and the drag calculation, for example, and design of the wings. From millimeters to decimeters, and if we want to go even further, we go down to the molecular level in this process. Typically, you are focusing on one thing, and you design an algorithm based on the model that fits a particular range of scales. You wouldn't use molecular feature in order to design the wing, but you would do that in order to look at the combustion processes, or if you were taking this airplane and do a re-entry in the Earth, you have very rarefied gas. You would do that. So typically, you have a range of methods developed based on physics, and they cover a reasonable range of scales, and then you develop numerical methods for those. So what you would talk about multiscale method is essentially either that the range is very large, as it could be in turbulence, and you have to do something there, or that you need coupling between different scales, different models in something. It could, for example, be, if you look at solids, again, there you could go from quantum mechanics all to elasticity, and it could be reasonable to if you do a problem that has crack propagation, that you would go into some features where atomistic model plays a role in the initiation of cracks and its propagation. If you don't use ad hoc formulas, via then plasticity and to elasticity on a larger scale, dislocation dynamics, etc. All of these things. So there are cases where you need to do this. And for example, if we take the fluids case, fluids are good to handle the water in here and the air in the bubble here. But what happens at the slip line is on the molecular side, it actually slips. So that could be of interest in coupling these two things together, etc. And there are many of the scales there. So that's sort of the background. Mathematically, we will just see, I will talk about it as functions, where I'll denote as the smallest scale of any energy with epsilon that plays a role, and overall size 1 of the domain. Typically, practically, we treat two things very differently, where the small scale or the high oscillations is all over the domain, or whether they are localized like in a boundary layer or something like that. That, or a stiff differential equation where you have something happening and then it's settled down. ODEs, there are methods for that for a long time that deal with that efficiently, mainly by changing the coordinates, or which is the same thing, gridding. So we will look at the other ones where the oscillations are spread over a larger distance. And we will also see, so you have these two, I'll call the one where they are localized, type A, so we did that, and the other one, which the ones where we focus on and where they're spread out for type B. Could come from a scaling. What do we need? A scaling law like this one, where the epsilon denotes that this is a multiscale function, and if it has this clean structure that it depends on the large scale and a much smaller scale. If it then is periodic, the function in the second class of variables, then we will get oscillations everywhere. If you have a law where it goes to a constant with respect to the second variable, we get a zero. We have a boundary layer, or initial layer in this case. So one thing is things like scaling law. The other one, to pin it down in a more mathematical way, is to get an expansion where scales are explicitly, like in a Fourier representation or wavelets or something like that. Overall, well, I'll think about the large scale as O1 and the small scales of interest being epsilon. Often, but not always, we will deal with problems that have scale separation. But we'll also talk about later in particular problems where that's not the case, where you have a full range of scales doing this. What's going on here now? They were there. Okay, so the challenge comes in just in order to represent these functions that depends on many scales, because over the many degrees of freedom, and the classical result, the Nyquist-Shannon result, says that you need, if you don't know anything more, you need at least 2 points per wavelength in the representation. So this tells us that the number of samples, the number of grid points, the number of elements, or whatever it is, needs to be 2 points per wavelength in each dimension. So that is the curse here. If you don't have anything more that you can't do anything about in this case. Then later we will come to the question about the cost in terms of floating point operations. Here we don't think about distributed calculation, just the number of floating point operation. And that could, of course, if you have an explicit method of a direct type, be of the same order, if it's highly accurate. But typically you need more than 2 points per wavelength in order to represent a process, like a differential or integral equation, to a certain accuracy. So the n would be the number that you multiply instead of these having 2, multiply epsilon inverse with. That would be the number of unknowns. And that depends, of course, on the accuracy you are interested in. And it also depends on how many wavelengths you need to deal with. And that depends on the problem. If you have an elliptic problem, you don't have the epsilon there. If you have a Helmholtz equation, you have it there, which is then pollution or the problem also with time-dependent problem, it adds on if it's not dissipative, etc. So it depends very much on that. And again, we have the number of dimensions, but then we also have R sitting there. It depends on what algebraic problem comes out after the discretization. Could be dense matrix, if we solve that by a dense matrix Gaussian elimination. R is 3, if it's an explicit method, R is 1. And we have something in between. So the third lecture will be attacking R. Now we are attacking the number of samples in the setting there. So sort of 3 types of problems, the methods in numerical analysis to handle these multiscale problems. So one here is where we try to use some feature in the problem in order not to need to follow the sampling of Shannon in this case, because we have a shortcut somewhere, and that's what we'll deal with today. The other one is where you have a representation in detail, and you want to repeat it over and over again, so then you try to reduce the problem in some way. Classical control theory, where you have maybe a big finite element problem, and you want faster input-output problems, and you reduce that by a number of different techniques. Could be more explicit, like these multiscale finite elements, or reduced basis. You can use wavelet compression in many other settings. For example, for images, which is down in the JPEG. So there you start with everything and reduce it. We'll not talk about that, but we'll talk about fast methods where you attack then the computational complexity rather than the number of degrees of freedom. So the lectures 1 and 2 will deal with this part where we try to do shortcuts in the overall numerics, and then fast methods more or less in the last two lectures in the series. So when it comes to these methods here, we have, and trying to understand what one can do in order to cheat a bit if we know something. One is then in information theory, since that was the one that told us we need to have these large number of unknowns. So what can one say if we know a little bit more? The second one is then more directed to the particular process that we try to approximate, or numerically or computationally. And these are things like the averaging we'll talk about now, homogenization and similar geometrical optics, or whatever it is, and try to use that as a guideline in numerics. Usually they are a little bit too restrictive in order to produce the problem. If that's possible, then we, of course, use a better model coming from mathematics. But if it's not, we just try to use them as guideline in this case. So that will be the two pillars that will develop the method for. So let's look at the information theory here. And that was first, I guess, developed by Engquist in Bell Labs, but not published in a reasonable way, more than an internal thing, and Shannon presented it first in this case. So that is, it says that the band-limited signal, so if the Fourier transform has compact support, then you can reconstruct it completely by the sampling rate. And they were sort of about thinking about signals. So per unit time, you can sample a certain, if you have a certain sampling intensity, then you can represent the band-limited signal, a signal that has a Fourier transform that is compactly supported in a way. And the limit, of course, is naturally the 2 per wavelength, because you can, of course, not find, you have to have better than that. This is 2 per wavelength, and you only get zeros, and you cannot get anything out of that. But you only need infinitesimally more density than that. And this is a formula that produces the function, reproduces the function completely if it is band limited, based on the samples over here times the factor, the sinc factor coming in. So this is the basic thing and tells there. So what about if we now look at this kind of scaling law that we had in the beginning, that is typically in certain parts of averaging and homogenization theory in its cleanest form, that we have the fast scale separated from the slow scale in a function, that you have a function that depends on 2 variables. So this I looked at with Christina Frederick in this case, and we would then assume band limited, otherwise we cannot do anything in terms of this theory, in both variables here, and then periodic in the second variable. So this is what we'll look at. So the idea there, if you do that, if it's band limited in the second period, you can do a Fourier series representation. If you then also look at the transform part, you would find that the coefficients here, which I forgot, there should be a C over there, has a support on a set that doesn't range all the way from the negative part to the positive here, but has gaps. So it will be looking like that. And the question is, can one benefit from that in a sampling? Not too hard to do. You could do that randomly to get it back with probability 1, but you have to do it in a stable fashion. So you have to get estimates on how the bound on the what you produce, a representation based on the measurements in this case, so that we'll come back to this part. But this is, it would be the challenge. And that has been looked at through history before, of course. So you had the original result that is then called the Nyquist rate that Shannon proved, or presented the proof of, which means this rate only looking at the convex hull of the full support in the case here, from minus support. So that's, and then there is a result, the Landau rate, already back in 67, where he proved that you cannot do better than this. And this is just essentially counting the number of unknowns that you need, the number of samples you need for the number of unknowns per unit time if you have a time series signal in doing that. So this is a 1-1 correspondent, and if you had more, then you can show non-uniqueness in the representation. So that's what he did. And then people have looked at different kinds of knowledge coming out for how the bandwidth is. And the first result was really by Arne Berling, which is my great grandfather academically. This is in his paper, so he didn't publish this more than in internal memo. But this came afterwards when they summed up his complete works in this case. So this was just that you have an interval, but the interval doesn't need to be symmetric around 0. So you take an interval anywhere, and then the basic Shannon result doesn't help you in doing this, but then you can do that. Then people have different widths where several intervals, where you have different kinds of sets, and the more general result right now stands that you can do a stable reconstruction, studied as a frame here, if the spectrum is supported on a set of finite measure. So the last part, and of course, all of these general measure was done by using an open cover, and then results of this type for each of each individual. So the question is, does these constant blow up or not if it becomes an infinite, if it's not bounded, but finite measure. So that it is. The thing is that all of these things do not have any information about how the sampling set would look like. So we have some result along this also, but the thing we were looking at was to have, first of all, a somewhat understanding about the stability constants involved. Numerically, one needs to think about that, and not just that there exists one. And the other one is, can that give a guidance how you do the sampling? And that's not there. So here is the result along those lines. So the thing is that the samples here, the sampling set here, if you have these points in the sampling set, the sampling set looks like this. So this is a discrete sampling where you have sort of large step sizes and small step sizes. The n here is the whole real integer, all integers here, and these are integers in a finite set. That comes from the fact that you had a band limited in the sort of periodic part in doing this thing. So if you do that and resolve large scale good enough and the small scales good enough, so you have these conditions on that, and you can go to the exact limit here in these cases. Then you get a stability estimates over here. So these would be the norms of the function, and that is bounded then. So this part is the important one, and you would like to have A bounded from below by the L2 norm of the discrete set that you're looking at. So we had the band limited, the bands looking like that. This just came from the original one. And here, yeah, okay. So we, yes. So we can take a look at how to do this thing. So we had this in the beginning. It's not too hard to say that you can then represent it, of course, because a band limited here. And then you have these sets bounded in some way. Let's say this. So the producing a proof of this is to use a Shannon representation where you only forget about everything but one periodic set here, and you do a periodic representation in over that way. And then you restrict the Fourier series, then you can do that for all of these shifts that are involved. So you have a number of shifts that resolves a periodic part of these things, and then you combine them in order to do all of these points. You get a van der Monde system, and you can use estimates that exist for van der Monde system to get the stability results and the final proof in this case. So that's it. And then you have a representation that tells you, well, I didn't have that on here. Yes, I do here. It has to look like this. the points in the representation. So you have a cluster of points that belongs to that resolves sort of the small scale, and then you have a cluster of clusters that resolves the other scale. So this is a stable way of doing that. You go to the limit, so you get actually the Landau rate in doing this. So that's the important part. You could go do this also in 2D, and we are now looking at case where you must know that it is periodic in the small scales, but other features, or it could be anisotropic or something like that. So we're considering this different parts, and that would only affect the sampling within these small boxes that are sitting there in order to do a different setup of the support in the Fourier plane in this case. So this would be a multiscale method that typically would come out of the traditional periodic homogenization theory. And then you can also represent the functions cluster-wise in this way, in a perfect way. So that's what we have over there. The other background is then from the mathematical way of simplifying equations depending on more scales. So symbolically, we can think of it as a PDE or integral equation that has a range of scales in them, and we are looking for what happens. Now, of course, numerically, we will have it.
Before you
yes.
go on this new topic, among the extensions, the analysis you did relies entirely on the Fourier.
Yes.
On lots of things which are known on band-limited functions.
Yes.
And so on. Okay. So typically, if you were to replace periodic by random,
yeah,
you would lose lots of structure.
Yes.
Except that some stationary function.
So all of that similar would be stationary random processes and functions.
Then you would need to build in some spectral information
mm-hmm.
from stationary process,
yeah.
and things like that exist. But I don't know in terms of analysis how far they're being pushed in terms of sampling. I'm not aware. But around signal processing,
there is a huge literature around that, and so some of the applications, of course, even that we have done, have been in the random setting. But this is hard enough once you do the numerics. That's right. But you're completely right. It's a different setting in there. And there is a process, of course. Then you would never gain anything out of this way of dealing with that. But I'll come back to the random case a little bit in the homogenization setting for, and that will be next time. What kind of results you can get in homogenization, even for the numerics. I mean, in this case. But here we didn't do that. Stayed away. Just talk to people who did that in this case. Stayed away from that. But that's true. You lose a lot of this. Okay, so the thing we'll take about is just a simple averaging type idea of dynamical systems. Homogenization will come up next time as one, and then there is, of course, many other settings in geometrical optics, whatever it is, where there is a well-established mathematical theory. So, for example, in this, when you try to prove something about this, a guideline would always rely upon some mathematical limiting theory. And then you would apply it in a situation where you don't know, for example, going from particle simulation in molecular dynamics via Boltzmann to Navier-Stokes type problems. In the latter part, you have a little bit, but from the beginning, there is no theory, so you have to just rely theory-wise and then use it as a guideline and not prove stuff about it. So this is what will happen. Okay, so this is it. So we'll look at the averaging part, and we'll assume that the system can be written in two parts, where you have the oscillatory, highly oscillatory part by itself. This is then unlimited when epsilon goes to zero derivative oscillation, and here you have something that where the derivative stays bounded, and the oscillations here feeds into there. But you assume, or you can prove, depending on what it is, the properties here, and again here there is a stochastic theory behind. I will look, when it comes explicitly, to a case where you have periodicity in this here. So this traces out periodic orbit, producing then the invariant measure that is needed for the process. So for now we will not go into the rich theory that exists in the generality, but we will assume this is doing on and take as an example where it's easy to prove in the case where that is doing that. So this is the other type of guideline that comes in as a background. So we will be able to try to mimic this in some way over there. And this is an example we'll use both how it's easy and how it will modifying it to be difficult. So we have here the V1, V2 is just an harmonic oscillator, a linear problem that produces the sine and cosine solutions. And then if we follow the averaging there, you would then get an equation looking like that for the slow variable, which was just the square of one of these variables. It will look like this, oscillatory with epsilon. And here, of course, integrating over time, it's easy to see what it is, and you get the slow solution, trivially in this case. This turns out to be working extremely easy to do numerically, but just perturbing it a little bit and a lot of headaches comes up. There is, of course, a similar thing we will come back to later in the PD setting. That is a good guideline for doing this, and that's homogenization, where you resolve the interaction between variable coefficients and the oscillations in the solution in a local setting over one period, and by solving a cell problem, which then feeds into a formula for the homogenized tensor over here, so that you get a problem that doesn't depend on epsilon at all, and then from the word of it, it mimics the homogenization in the setting there. So now we come to the numerical approach to do these things. And so we try to follow this, and I'll discuss that next time, and that we started with Nunn a long time ago. And the purpose was, of course, to couple a macro-scale model to a micro-scale model in a way that, in the ideal world, would be the fidelity, the accuracy, and the use of a number of unknowns of a macro-scale model, and the fidelity on the micro-scale, the details on the micro-scale model. So the idea is that you produce a macro-scale model, you design that first, and if you then have some missing components in there, like the homogenized tensor, like the average equation, you would pick that up from the microscale model. So overall, there would be a method that only works on the macro scale. The idea to focus on the macro scale was that, which is sort of, you do that first, and then you feed in microscale information, is that you get control over the macroscale process. If you do it microscale process and try to extend it, which exists in many different ways, where you aggregate molecules in order to have macromolecules that works, etc. In many settings, it's difficult because you could end up with an unstable process, in particular in the differential equations setting, so that you extrapolate the microscale process over longer time. Talk more about that later. And that will then not end up with a stable process over here. Here you have control over the overall process. You can see that you need a certain CFL number or whatever it is, even if you have this coupling setting. So that's what it looked like. So for the ODEs, then you had on one hand, you have the system here where you produce an averaged equation. And if this is a periodic with this guy for frozen U, then you have a system looking like that. And then we know that the correct sampling for a stable setting, even with the optimal sampling rate overall, would look like that. So you cluster the sampling here. So it's natural to put these two together in a numerical algorithm, which was over here. So we did it explicitly, it was discussed in the papers with Nunn, but explicitly in the theory with Richard Tsai. So you have then a coarse solver where you think that you know the forcing, the effective forcing, and you step size according to the variation of the slow variable, so the order 1 scale in our case. But then you need the effective forcing, and that you do by calculating on the fine scale. So this is again a numerical method. Think Runge-Kutta in both cases, for example, where you do a calculation long enough so you can integrate over here in order to get the average, which you then feed in. So you take a step, you need the new force, you do a calculation in detail to get the force a step further, etc., and build it in. So this would be the overall structure in the system. So you have two local processes, and then you have a non-local coupling in between those when you do the calculation. And that works well in many, many cases, not all. So early case, which is natural, it's Kapitsa pendulum. Nobel laureate, not for the pendulum result, but this was seen as sort of a control theory thing by him, controlling on the atomistic scale. So you have a pendulum that if you take the pivot point and oscillate that rapidly, so this is not adaptive control in this case, you have this given, then you would have a force from the oscillation in such a way that the pendulum will be stable when it's pointing up. And it will swing back and forth over here. This would be the equation in that. And then you can do a numerical simulation following the recipe that before. So you do a calculation involving a few oscillations over here. Then you get the force on this. You have gravity, but the other force is strong enough for it to move up in this direction. So here the movement on the larger scale, and if you see, this is a full simulation, but it will be accurately represented even if you do just burst of calculations on the force in this case. So this is an example which is a bit tougher, and one where there is no other approach, essentially. You cannot do this in any other way. So you have a oscillator that is a nonlinear oscillator that is stiff in itself. So this has two scales, an epsilon scale and an epsilon square scale in this case, or depending how you reformulate. Here is one and one over an epsilon. So you have the solution in the phase plane will move over and then rapidly jump to this curve here and then rapidly goes up. So you have something that a stiff solver does very well, so you need to do that. And if this is an oscillator, then all the theory of the methods that are being developed, exponential, Magnus methods, etc., for oscillatory problem doesn't work, because this is not a good approximation of a constant coefficient of a harmonic oscillator. So if this is the main thing that drives the engine of the oscillation, then this is, you have to resolve this numerically, and this is then the only thing to couple it if you then would have a problem that has a slow scale, a really slow scale. So if you couple it to a harmonic oscillator, you get a phase locking phenomena. So over the long scale, they match up and lock phase. So what you do is that you do a calculation where these nonlinear oscillator and the harmonic oscillator go together and get an overall force that you take a larger step, so that with time you can see the phase locking property coming out of the system. So this would be the challenge in doing this. So most of the proofs in this process will be we have the macro solver, we have the micro solver, and then we have the coupling process. And the coupling process you need to compare with an effective equation. So you assume that we have an effective equation, and that's where, let's say, molecular dynamics fails in this case, mathematically. Here you have the averaging. So this is the averaged equation and its numerical approximation. So the thing you compare is the numerical method coming out of this process of coupling and what would happen if you directly would approximate the effective equation over there. And the coupling is via the theory then of averaging here. So there are three things you need to prove. One is the convergence on the macro scale, convergence on the micro scale, and then the coupling. So these guys, of course, are trivial. in the sense that there already exists a numerical theory for stability and accuracy of those, and that's what you can use. So the new features in here is then the coupling. And one important component in the coupling here is then how well the average is described if you have an accurate solution on the microscale. So you do that by approximating the integral here by some discrete methods. And typically you use a kernel that has certain properties, certain regularity, and then certain moment condition in doing that in the approximation. And then you could see the different parts in the approximation where the errors comes in the proof. So you have the error coming from the macro solver, depending on the order of accuracy for the method and step size, the micro solver, the order of accuracy relative to the epsilon scale, and then the number of these that comes in through a macro step. So this part will be the micro solver actually, but of course it accumulates the error, so you have to have this factor. And then you have the integration. There are two sources of error there. If you know, we looked at the periodic case also here. So if you know the period, then you get rid of these errors, but typically you don't, because you want to use it, as you mentioned, in a case where it's not periodic. So at least it should work in the periodic case, but when you don't know the period. And so you have one endpoint resonant because you don't stop exactly at the end of a period. You will stop somewhere somewhere wherever it is there, and that is the endpoint resonance error here. Of course, it's better if you take a very long range and average over, because the endpoints play less of a role, and it depends on the oscillation size in this case. And it depends on the regularity. If you smooth that out at the end, then the regularity, of course, helps you. So the idea is to have a very regular thing. And then if you take a very long range, then the slow scale will not be exactly represented at the point you're interested. You want the force at a particular point, but if you average even in the slow scale, of course, you get an error in the averaging. So you do a moment conditions so that it is accurate for polynomial up to a certain degree. And that's the best way of doing it for these guys. So this is possible. So all of that is there. But it's one thing that, so this would work for certain problems, linear problems, and where certain resonances are not there. So you could have classes of doing that. I will not go into the details of those. And it wouldn't work if you would use the microscale all the time and then just do the integration here. Of course, you don't want to do that. The idea is to only use a microscale to get the forcing there. But if you use it so you don't need to restart. So the question is, when you restart that, you have the slow variables correctly up to numerical accuracy, because they are carried by the core scale and the core solver. But where should you start the microscale thing? If it is ergodic, it doesn't matter. Or if you have a dissipative process, so it dies away, so the missed starting values, it doesn't matter. But if that's not the case, then that causes problems. So even in simple settings, what could happen, you have the fast motion on some manifold here, and then the fast solver could contain slow variable, so to speak, so that this donut changes, and then you are starting off on the wrong donut at the new part. And we'll see that explicitly. If you take our simple example, what we had here was the V1, V2 was an harmonic oscillator. Ignore these terms here. And then it was spinning around a circle, and then these oscillations over here averaged out, gave an exact solution here. You can do that and start off again. But if we add this little term here, then it doesn't stay on a circle. It will be a spiral out. And there is a slow, even in these epsilon inverse equation that looks like only fast variables, there is a hidden slow variable, namely the radius that increases over here. And that will then mean, because the averages when you do this is 0, so you don't see that in the simulation. You will spin around and then you will still stay where you were, and this order 1 scale expansion is not seen there. So you have to collect all slow variables in here, and then you can prove convergence nicely. You could do that by rewriting the problem in coordinates so that you only have the angle that is the fast variable. Then it works fine. So that is the first thing to do was to understand this, that you can cluster the thing. The second problem over here is how to restart. Very often in physics, you would have processes which calibrate themselves. You get back to a Maxwellian type distribution or something, or there is some dissipative process coming in. So you know that you can get a closure within, from other reasons, with mass, momentum, and energy, for example, or something like that. But if you don't know anything a priori, this is a big difficulty. So one can think about different ways of dealing with this thing. One is that you derive certain averages that you use as control of this. That is, for example, heat bath in molecular dynamics. You would do that so that certain things do not get, you can control the fast variable, so to speak, in this way. The other would be to derive in some way a complete set of slow variables, and then you can start on the fast variable wherever you are, like in the case where you only have one of them that you had in the early case. Then you, instead of dividing the solution variables, the dependent variables, you can divide the forces up in slow and fast. We'll come to that. There is also a way of looking at the phase plane maps and do calculation all the way, but use this process only for the core solver in a parallel formulation that was developed here, this city. But I'll not go into this here. But this is quite promising in a way. So you use this machinery just for the slow one, but then you actually solve, which is challenging for a Hamiltonian system, and then you solve in parallel, time parallel then. So if you take this problem over here, one can add, for example, this as a new unknown, derive equation for that, and force this to be accurate at the end of the step when you reinitialize. So and this is possible. What was difficult in doing this is a calculation where you have to be very, very accurate. So the calculation on the micro scale and on the macro scale for these control units turned out to be very sensitive. So it should look like this. This is like the Kapitsa pendulum, but it's two springs or three masses and two springs that are in symmetry. And you get sort of the angle would in between here, and the distance between these guys go back and forth in the same way. Same mechanism as the other, but here it's freestanding. And it's very easy to, instead of converging to this, to do this. And for larger thing, we look at that in molecular dynamics setting. Seems to be not so efficient. What worked well was to determine a complete set of slow variables. So of course the null space of the epsilon inverse part, which was slow to start with, is obviously a slow variable. The amplitude of the oscillator, if you have an oscillator of the type that you have, is a slow variable, and the phase difference between the oscillators modulo some factor is also a slow variable. So in our case, the slow variable here, because it's a null space, and here you have the R, the radius over here, which is the amplitude of these guys, our slow variable. And then you reformulate it. So you can do an algorithms by deciphering all these parts in order to get the slow variable. And the example was that I did with the nonlinear oscillator coupled to the linear one for phase locking. That was done this particular way. And as a typical problem, this Fermi pasta ulam has been used as a challenge for oscillatory numerical solutions. So you have a stiff linear spring and a weight, and you have a nonlinear spring that is weaker, and you couple that with stiff spring. And they wanted to show, actually, originally, that you get an even distributed, ergodic distribution. So if you kick one of these and it starts to oscillate, then with time it will spread out to all of them, but it didn't. So they did calculations, and it happened that the energy moves around between the different springs over here. So this is on the slow scale. And so we have done that with more springs, and then you can do with other techniques in doing that. And all of these things is just one fast variable. If you then have the amplitudes, the slow strings, and the difference between the other being the slow variable. So that's driving here. So this is a way of doing it. And this is done by bursts of calculations, get effective force, and then restart doing the process there, so that you can calculate in the original variable, but when you restart it, then you go back to this true slow variable, get the new starting values, and then transform back, as was given by this algorithm that I had before. You need to do certain things. These are then you would like to use geometric integrators, and you cannot do the starting. So if you have a time reverse equation, you will solve in both directions to get symmetric setting, etc. So it's a lot of technical details that doesn't affect the overall process. But you need to do that so that you get an overall symplectic algorithm instead of something that dissipates when you do that. The third way of doing this is instead of looking at the variables, fast and slow variables, is to divide the forcing function up in a slow and fast part. So in our case, you would have this belonging to the fast part and the other extra variable to the slow part. So in this way, the initialization is not necessary. And that was done by Marston and company first, and then there is a Van der Eyden and company worked on the idea of doing this. So the idea is that you take a long step where the part of the forcing that is not depending on epsilon directly is there, and then you take a short step where you take the full function, including the slow and the fast part, just the slow, the fast, etc. And you do this there. So this there is no restart in this. You have all the things doing that. So the idea in the proof would be here that in order to prove it, you have to use this, the setting. But when you do perform, you don't need to do this process of dividing it up in slow variable and fast variable. Here I have to do that where this is a ergodic process here. So precisely as we did, but just for the proof. And then you have this particular setup over there. So what you need is that the fast step here resolves the epsilon scale. You need also that the large step here cannot be order 1, as it was in our case, because it only acts on the slow scale. But you also that also has to be related to epsilon. So when epsilon is smaller, it has to be smaller, because now the fast scale that we integrate over, that produce the invariant measure, that has to come in often enough to support the integration. So this is more or less like a Monte Carlo integration coming in, and it's more like a Monte Carlo on the stochastic part, coming in regularly. So that this step is much shorter in the setting in order to get the proof to work. So that's being there. So now it looks funny, because we are back in, if we go back to the information theory part, it looks like we violate this, because this guy is now not in these bursts of sending. This is more like a Shannon thing, and we are beating the Shannon theorem with the same kind of sampling. The fast sampling is just done on a uniform mesh in this way. And that seems counterintuitive. But if one analyzes their method a little bit more, it turns out, so what they actually approximate is not with the true epsilon. It is with a modified epsilon that fits this sampling rate. So what they approximate is actually, of course, when epsilon go to 0, then you get the same limit as if 100 epsilon go to 0. And then what they do is they do 100 epsilon instead. So you get high oscillations because what you're doing, you're resolving a problem that has a much longer wavelength than what you have. And the scaling comes in because you only use the microscale so sparingly here, and you don't know any averaging. So what happens is that the new epsilon is scaled by the ratio between these two here times the other epsilon. So it is like doing a high Reynolds number calculation with a low Reynolds number. But many problems, the flow is quite similar, but of course not if you're interested in it. Now, you could then learn about what we thought about in the proof from information theory, and then you can improve this approach by having a gradual method where you stretch it out over here and then concentrate it. So you map an equidistributed microscale to something that clusters up, and you get an averaging here, which means that for this kind of problem, like this oscillator we had, then you could actually do a good job. So if you take a more complicated equation, this has been in the literature for doing that, then you cluster it. So this would be the oscillation and that you will have in general. But if you cluster it and only uses the value here, which are the circles, you are doing an accurate job with the correct epsilon, so to speak. The wrong epsilon gives large oscillations here. So if you're interested in doing some averaging or whatever you do, sample this, you get an epsilon error. And if that means something, then of course that is very much important. And that was it about this. We talk about the general thing, that it's costly in general, and its guideline that we mentioned over here is one in information theory and one in one of these mathematical theories. And here it was averaging that was the point. Then we saw that there are always issues that comes up, like the restart over here. And later, next time, we'll look at different kinds of application where one needs to tweak and adjust the methods in order to either be able to prove something or be able to show approximations that work well in practice. Thank you.
Thank you very much.